So notice that Frobenius' theorem shows us that there does not exist a three-dimensional associative division algebra over the field of reals. And so Hamilton's search for a three-dimensional algebra with the same properties as the complex numbers was in vain. However, it was not completely fruitless, as it led to his discovery of the Quaternions, where the Quaternions is a non-commutative associative division algebra over the reals, that is a four-dimensional algebra. Now, Frobenius' theorem relies on two results that we have not yet looked at. One is the fundamental theorem of algebra, and another is a theorem known as the Cayley-Hamilton theorem. And so we will have to postpone a proof of Frobenius' theorem until we see those results. Now, the Quaternions is not a field, rather it is a skew field, and so there are some interesting results for or implications for solutions of equations in the algebra, the Quaternion algebra. So let the Quaternions be considered as elements of the form x sub naught plus the three-dimensional vector x, where x sub naught is a real scalar and the three-dimensional vector x is a three-dimensional real vector. Then the equation x squared plus 1 equals 0 has infinitely many solutions. In this algebra. So proof. Let x be a quaternion. Then x squared is x sub naught plus the three-dimensional vector x, the quantity x sub naught plus the three-dimensional vector x squared, which is x sub naught squared, plus 2 times x sub naught times the three-dimensional vector x, plus the cross product of the vector x with itself minus the dot product of the vector x with itself. The cross product of any three-dimensional vector with itself is the zero vector, and so we have x sub naught squared plus 2 times x sub naught times the three-dimensional vector x minus the dot product of the three-dimensional vector x, which is x sub 1 squared plus x sub 2 squared plus x sub 3 squared. And so the real part of x squared is x sub naught squared minus the quantity x sub 1 squared plus x sub 2 squared plus x sub 3 squared. And the imaginary part of x squared is 2 times x sub naught times the three-dimensional vector x. So let x squared be equal to -1. This is the same as -1 plus the 0 vector. Then the real part of x squared, which once again is x sub naught squared minus the quantity x sub 1 squared plus x sub 2 squared plus x sub 3 squared, is equal to the scalar -1. And the imaginary part of x squared, which is 2 times x sub naught times the three-dimensional vector x, is the 0 vector. Now notice that the three-dimensional vector x cannot be 0, since this implies that the real part of x squared is x sub naught squared, which is equal to -1, and there does not exist a real number x sub naught such that the square of that real number is equal to -1. And so the imaginary part of x squared, which again is 2 times x sub naught times the three-dimensional vector x, is equal to 0. This implies that the scalar x sub naught is 0. And so the real part of x squared is the negative of the quantity x sub 1 squared plus x sub 2 squared plus x sub 3 squared, and this is equal to -1, so that we have the equation x sub 1 squared plus x sub 2 squared plus x sub 3 squared is equal to 1, and this is the unit sphere. In real 3 space. And so every quaternion of the form 0 plus a three-dimensional vector x, where the norm of that vector is equal to 1, is a solution to the equation x squared plus 1 equals negative, or correction, x squared plus 1 equals 0. And there are infinitely many such vectors. Now, a major division of algebras over a field is between associative and non-associative algebras. But the term non-associative can be somewhat misleading, because in the literature the term non-associative often means not necessarily associative. And we'll be looking at two general types. So, a new definition: a Jordan algebra is a commutative but not necessarily associative algebra over a field F such that vector multiplication satisfies the following identity: the quantity xy times x squared is equal to x times the quantity y times x squared, and this identity is known as the Jordan identity. The Jordan algebra, or Jordan algebras, are named after the German mathematician Ernst Pascual Jordan. So notice that an associative algebra necessarily satisfies the Jordan identity So a commutative and associative algebra is a Jordan algebra and so, for example, the reals and the complex numbers are real Jordan algebras. And any associative algebra can be made into a Jordan algebra, as we will show in the next example. So the Quaternions is an associative but not commutative algebra over the reals. So define a new operation, a type of multiplication, x circle y, to be the sum of the products x times y plus y times x over 2. Notice that x circle y is the same as y circle x. That is, this is a commutative type of multiplication. Now, the normal product of quaternions, x times y, is the sum x sub naught times y sub naught plus x sub naught times the three-dimensional vector y plus y sub naught times the three-dimensional vector x plus the cross product of x and y minus the dot product of the three-dimensional vectors x and y. And the product y times x is x sub naught times y sub naught plus x sub naught times the vector y plus y sub naught times the vector x minus the cross product of x and y, since the product y cross x is the negative of x cross y, minus the dot product of x and y, the vectors x and y. And so x times y plus y times x in normal quaternion multiplication is 2 times the quantity x sub naught times y sub naught plus x sub naught times the vector y plus y sub naught times the vector x minus the dot product of x and y. And hence the product x circle y is the quantity x sub naught times y, or x sub naught times y sub naught plus x sub naught times the vector y plus y sub naught times the vector x minus the dot product of y and x. And again, this is now a commutative operation, a form of multiplication that is commutative. So now we need to show that this satisfies the Jordan identity. Now, the quantity x circle y, circle x squared is the quantity x times y plus y times x over 2 times x squared plus x squared times the quantity x times y plus y times x over 2, all of which is divided by 2. And so we have x times y times x squared, where I'm leaving out the parentheses since multiplication of quaternions is associative, plus y times x cubed plus x cubed times y plus x squared times y times x, all of which is divided by 4. And x circle the quantity, y circle x squared, is x times the quantity, y times x squared plus x squared times y over 2 plus the quantity, y times x squared plus x squared times y over 2 times x, all of which is divided by 2. And so we have x times y times x squared plus x cubed times y plus y times x cubed plus x squared times y times x, all of which is divided by 4. And this is the same as x, the quantity x circle y circle x squared. And therefore the quaternions with the operation x circle y, which is x times y plus y times x over 2 for the normal products of quaternions, is a real Jordan algebra. Now the operation x circle y, which is defined to be the sum of the products of normal multiplication divided by 2, where we take the product x times y and y times x, is called the anti-commutator and every associative algebra with the anti-commutator is a Jordan algebra. Now notice that if x times y is the same as y times x, that is, if multiplication is commutative, then the anti-commutator x circle y is 2 times x times y over 2, which is x times y. And so the anti-commutator does not change multiplication for commutative algebras.